these structures carefully. What did you observe? Here, I have shown two complexes. Both are tetra-coordinated. However, one is square planar, the other one is tetrahedral. My question is, how will you account for the different geometry of these two complexes? They are having same coordination, but they have different geometries. To explain the structure and bonding in coordination complexes, different theories have been proposed. In this class, you will learn about valence bond theory. This was proposed and developed by Linus Pauling. This theory, it will help you to predict the structure of coordination compounds. We will proceed with an example, say a cobalt complex. Here, in this complex, cobalt is in +3 oxidation state and it has an electronic configuration of 3d6. Here, 4s and 4p orbitals are vacant. According to valence bond theory, the central metal, it will provide vacant orbitals equal to the coordination number to accommodate the electrons donated by the ligands. These orbitals will undergo hybridization to yield a set of equivalent orbitals of definite geometry. Here, cobalt forms D2sp3 hybridization to accommodate 6 ammonia ligands. Hybridization is in fact a mathematical manipulation of wave equations for the atomic orbitals involved in bonding. The 6 pairs of electrons, one from each ammonia ligand, occupy the hybrid orbitals, giving rise to octahedral geometry. As all electrons are paired, this complex has diamagnetic character. Also, this complex has formed by utilizing the inner 3D orbitals rather than outer 4D orbital. Such complexes are called inner orbital or low spin or spin paired complexes. However, there are complexes where outer orbital, say here 4D, is used for hybridization. This results in sp3d2 hybrid orbitals. The 6 pairs of electrons, each from 6 fluoride ligands, it will occupy the hybrid orbitals and gives octahedral geometry. Such complexes are called outer orbital or high spin or spin-free complex. Meaning, ligands, they can use n-1d, ns, np or nd orbitals for hybridization. This results in different geometries based on the coordination number as well as the nature of the central metal. These hybridized orbitals, say sp3, dsp2, sp3d or sp3d2. They overlap with ligand orbitals which donate electron pairs for bonding and they result in geometry of that specific complex. Now let us discuss how magnetic moment of a coordination complex helps to predict its geometry. The magnetic moment of a coordination compound can be measured by magnetic susceptibility experiments using equivalence. Such studies will give information about the number of unpaired electrons present in the compound. This can be utilized to deduce the structures of complexes. For instance, magnetic susceptibility studies, it revealed that the tetrachloronickelate 2 is a paramagnetic complex. Looking into the electronic configuration, the paramagnetic nature, it can be explained only if this 3D orbital, it remains unpaired. This results in a sp3 hybridization and hence tetrachloronickelate 2 is a tetrahedral high spin complex. On the other hand, the magnetic susceptibility studies revealed diamagnetic nature for tetracyanonickelate 2 complex. Look at the electronic configuration of nickel ion. The diamagnetism could be explained only if the unpaired electrons in the 3D orbital get paired up. This results in a dsp2 hybridization and hence a square planar complex. Although valence bond theory successfully explains the formation, geometry and magnetic behavior of coordination complexes, the theory suffers from certain drawbacks. Valence bond theory could not explain the color exhibited by coordination compounds. According to valence bond theory, tetraamine copper complex has a tetrahedral structure. However, X-ray analysis proved it is square planar in nature. Further, valence bond theory failed to interpret the magnetic behavior as well as the thermodynamic and kinetic stabilities of coordination complexes. Also, it cannot distinguish between weak and strong ligands. Now, on the basis of valence bond theory, can you predict the geometry of the complex if the magnetic moment is given?
Manorama Horizon. Learning made simple.